Okay, good afternoon, folks. Hope you guys doing all right and had a fantastic break. And also, I'm hoping you received my email about the final exam and option available for swapping one of your midterm score to your final score, better or worse. Okay, so you need to decide that before final day. So you have about a week to decide on that. Once you decide, you send me email, okay? So and that's that. So now so today gonna be our last class in terms of introducing new materials. So next class gonna be review and final. Hey, we almost done with the semester. And I just saw there is the FCQs up for a long time and it's going to be closing tomorrow. So most likely I'll send you one email this evening or tomorrow morning reminding that you guys participate. Okay, everybody participate. And there may be incentive if almost everybody participates, and detail gonna be on the email. Okay, so now let's go back to the lecture here. So we started talking about why quantum mechanics was necessary and how some of the experiment at the late 20th century, not late 20th but 19th century or beginning of 20th century, some of these experiments were not, the result of those experiments were not or could not be explained by using the knowledge of the physics at that time. So we talked about those experiments and how the energy needed to be quantized to explain those experimental results. So that's what we learned in last class. And by the way, today my chat window, I cannot check my chat window, okay? Unfortunately, my setup slightly changed, and because of that, I cannot, see the chat at the same time unless I actually go look for the chat, okay? So sorry about that inconvenience. And if you are trying to talk to me, please turn on your microphone and talk to me directly, okay? Okay, so now, with that said, so what happened is, at the same time around, there was this, I wouldn't say same time around, but they explaining the atomic spectrum. The spectrum we can see from the light coming out from the object was a bit difficult, and how the atom is made up of, or defining the atomic model, that was also difficult. And all those phenomena were successfully explained by using this quantum idea. So today we're gonna just go through that and talk a bit in detail about the Bohr's theory and how we explain the emission of light by using the quantized energy theorem, okay? So that's what we're gonna be doing today. So what was the atomic model? So before the electron was discovered, which is 1897, so kind of late 19th century, right? So when electron was discovered, the idea is that the smallest identity or entity, I should say, is an atom that was broken because there was something coming out from inside the atom. So there must be those things, including the newly discovered electrons, okay, must be inside. And at that time, it was known that atoms, they are neutral. So since negative charge coming out, that means there also must be positive charge. So how do we explain that kind of atomic model? So for that, this model was developed. So in the lab this semester, you've been learning about modeling scientific phenomenon, right? So this is an example how you actually start building model and keep on modifying that until you get, or you could explain all the experimental observation. This is a very good example of that, okay? So here, so you see the negatively charged particle, electrons coming out, so there must be positive charge inside. And since the atom as a whole was neutral, the amount of positive charge and amount of negative charge must be same, right? So to explain that, to visualize that, so they come up with this a model of the atom where there are these floating negative charge on a, like let's say in a pudding that is positively charged. So it's called plum pudding model, okay? Or you can think of this as cookies with the M&Ms embedded on that, okay? So that was the model. But later, when one experiment was done by the Rutherford, where a very energetic charged particle were bombarded into the very thin film of matter, okay? As you can see, there is this thin gold foil, right? So it's a very thin, and there are these alpha particle. These are charged particle that gets emitted from radioactive materials. So they are very fast moving and they are relatively large in size than the electrons, okay? So they were large, they were energetic, and you are bombarding that. So it's like you are shooting a paper, thin paper, with, let's say, bullet. Okay, so you are doing something like that. Okay, so what do you expect? You expect all bullets to just penetrate through that paper uniformly, or just reverse back, depending on situation, right? So these particles being energetic and massive, we expect them to just penetrate through that, okay? But it was surprising to see that some of those bullets were bouncing back. Most of them were, passing through, but some of them were just bouncing back. So what's happening? It looks like there is some hardy stuff in that paper, in this case, in this thin film, right? So these were positively charged particles that were being bombarded. So they are getting repulsed, like pushed back, turned back. So that means there must be a massive positive charge there as well inside, okay? So now the plum pudding model of the atom had to be modified because the positive charges are not everywhere uniformly distributed, just like you would assume in case of plum pudding, right? but rather there must be some spots where there are positive charges and not so many, like those positive charges are not everywhere, but at some spots, okay? So that means positive charge is like that. So what are electrons doing? Negative charge is doing. How do we make the model? So since positive and negative charge attract each other, so one idea was to use this planetary model. We already knew the gravitational force between planet and the sun makes this planet lighter object compared to the sun go around the heavier object, which is sun. So similarly, this model assumed that, okay, these electrons are just orbiting around the positively charged heavy particle. So that's how this came, okay? So this model came in existence, but there was this problem, okay? That when these charged particles are moving, going back and forth, oscillating, from the classical theory, what we knew was that the charged particle should emit the energy, okay? They should emit the energy. So once they become less energetic means they are moving slower. Once they moving slower, they should spiral down to the positive charge, right? When Earth, for example, is moving around 30 kilometers every second, 30 kilometers per second, folks, nearly 20 miles per second around the sun. If Earth were to slow down, uh, what's going to happen? It may just get pulled down by the sun, and it may just fall into the sun. So same idea here, since this force between positive and negative charge. So if negative charge is losing energy, it may soon spiral down, right? It should soon spiral down. So that was the idea. But they were not surviving. So there was this problem with this model, okay, this planetary model of atom. So that's where comes the idea of this emission of light from the atom, energetic atoms, okay? And the light coming out, we call that spectrum, and we learned that in electromagnetic radiation chapter. This spectrum could be invisible and visible. Visible from red light to blue light or purple at most, but there are other whole spectrum that's coming out. So where do they come from? Okay, so the spectrum was observed, and those hot gases showing the emission spectrum, that shows they have a particular value of wavelength. They are discrete in nature. So if this electron were just spiraling down, then they should be emitting frequency or the wavelength, all sorts of wavelength, okay? Rather than giving this discrete. So how do you explain that, this discrete nature of the spectrum, okay? So this is the spectrum from the Mercury, you can see on the screen. And you have these different colors of certain wavelength. So this is mercury gas is inside the fluorescent. Remember the tube light? Probably you still have a tube light. If not in that very long form anymore, it may be in the a bit spiral kind of form in, in a smaller enclosing. So we still use them. So first it was filament, right? Filament light bulb. And then came this, the one with the mercury gas inside. We call that a CFL, I think. And then came the LED. So LED started just a few years back. So that's the spectrum coming out from the mercury. But when all light mix up, all color mix up, it becomes white, and that's what we see, the white light we see, okay? But what happens? If we were to do a careful observation, what you will find is it has this distinct wavelength of light coming out from there, okay? So this is an example of such spectrum. So now the challenge was to describe why, where this is coming from, and how can we tell which line and what wavelength and so on, right? So there is experimental observation. Now we need to come up with the theoretical model that can describe what's happening when we are observing by doing the experiment. So if we cannot support with the theoretical model, what happens is, are we observing the real phenomenon or something different happening there, right? So if theory supports the experiment and vice versa, that's when it becomes, the established scientific principle. So anyway, so that's the challenge. And as you can see, you can think of this as a tube light here, right? You can think of this as a tube light here. So in that case, what's happening? We supply very high voltage at the terminal of that tube, and these atoms, electrons, become excited, become energetic, and they start jumping on and off. And in that process, they are emitting this kind of spectral line, okay? So now, how do we actually mathematically calculate and get those values, for example, okay? How do we verify that? So just like we have emission spectrum, there was this observation of absorption spectrum as well. So what does it mean? So a certain element, when gets excited, it can emit certain wavelengths, right? So that's the emission spectrum. Now, if you pass those wavelengths, radiation with those wavelengths through those materials, what happens? They also absorb those exact wavelength. And what you find is you find those wavelengths missing. So it is kind of opposite of the emission. So that's another interesting observation. So you see those certain number of wavelength missing here as well, okay, in this experiment. So by doing heat and trial, by observing, making observation with different wavelength in a hydrogen atom, what happened is Rydberg came up with this equation. So this equation was just through the heat and trial method. So you try to rearrange the equation several different ways until you get the number you are looking for, okay? That's what heat and trial method is. You do the experiment, you observe the value, and you try to write down the equation. Better way is to start writing equation from the very first principle. So that means from the physics law you already know, you start building from there, combine different parameters and modify that equation and come up with the new equation, and that's the discovery. That's how discovery is done in physics. Okay, so this equation worked. Okay, was able to describe these wavelengths coming out from the hydrogen atom, but there was no theoretical basis for this equation. So in this case, in this equation, what you see, this is the wavelength that's coming out. Let's say you want to find. And there is this some constant, a number, okay? A constant number determined by the experiment. And there is, again, this number indicating that the energy level. So remember how these electrons are orbiting around, right? And then outermost electron, it can absorb energy and can jump to the higher levels. So the n is the number, those higher level, and they are jumping from n is equal to 3, 4, 5, 6, and so on to the n is equal to 2. So this n is the line, or let's say the state at which these electrons are jumping down to, from could be 3, 4, 5, okay, n is equal to greater or equal to 3. So once you plug those in, for example, when you plug n is equal to 3 here, you're going to get 1 over lambda is r, and 1 over 2 square means 4, minus when you put n is equal to 3, it becomes 1 over 9, right? And then what happens? You calculate the wavelength, and magically, what happens? This wavelength turns out to be, let's say, the red light, wavelength of red light you see around 650 nanometer. Okay, of course, this R is this number. So that's how this equation is used. For example, use n is equal to 3. Okay, so that was n is equal to 3. Now use n is equal to 4. And then what happens is that, oh, let's see. So n3, so that becomes smallest number here means largest number that being subtracted. So yes, looks like yes. So that's how you get 1 by 1 of each of, wavelength of each of those lines coming out. So plug in n is equal to 4, replace this by 16, that means n is square means n4 means n is square 16, and then you get another wavelength and so on. Okay, so that's great, it worked. But as a curious mind, as we all human are, we want to know, oh, where did this equation come from? Can we derive this equation from the basic principle? And that's what actually Bose did, okay? By modifying that, so that's what the Bose did. He used the quantized model of the energy in this planetary model, and then was able to successfully derive the equation to explain those spectrum. So that was more complete work. Okay. So here, as a, to show you how things are done in science, and that's the beautiful part of science, or physics, I should say here, is that how you start from the things you know and you keep adding the new information and then come up with the totally new theory. Okay, so that's how the discovery occurs. One way, you do the experimental observation, you observe new thing and you try to describe that. Another way, you just use that mathematical models and come up with the result and do the theory, or try to do the experiment to verify that. And both way, they are kind of equivalent works. So here, Bohr is trying to verify what was being observed. Okay, so he was developing this theoretical model to explain the experimental observation. Okay, so here he starts from the Newton's law, Newtonian physics, and Newtonian physics, I'm pretty sure you guys still remember, right? So net force is mass times acceleration, and if something is moving in circle, A in circular direction or radial direction is B square over R. So what is net force here? So for the case of planet and sun, that's the gravitational force between sun and planet. Here, positive and negative charge. So it's the electrostatic force between positive and negative charge. So that means this force is the Coulomb force between positive and negative charge, right? So you start from the basic law you already know, okay? And the force is the Coulomb's law here. Remember, Coulomb's law means K Q1 Q2 over R square. So Q1 is value of one charge, means let's say charge of an electron. And another charge, which in this case is proton. Remember, for a hydrogen atom, there is just one proton inside, and that's the positive charge we have. So the charge is still E, the value is still E. Yes, one is positive, another one is negative. So because of that, there is attractive force. But the value is just one value of Q1, another value, both Q1 and Q2, they are E and E. So that means that's what I'm writing here. And what is R? R is the separation distance between them. So in this case, R is the separation distance between positive charge and the electrons that's orbiting around that positive charge in the hydrogen atom, okay? And the hydrogen atom, when it gets excited, can move a little farther away. So that means value R is not fixed, okay? So value is changing. So because of that, what's happening is we are writing R, but we have subscript N. So if it is at the very first orbit, then N is equal to 1, or we can say R1 is the distance, and so on. So very first orbit means, in that case, that's going to be the ground state of the hydrogen. Okay, so proton here, and it is at ground state. it is means electron is at ground state. So that's the distance between proton and electron, means that is also the size of hydrogen atom. So that's how big the hydrogen atom is. Okay, so if you can calculate value of that R1, that means now you can tell how big an atom is. Another interesting thing there. See that? So you start from basic here, and then you simplify this equation a little bit. So E times E means E square, right? And there is Rn and there is Rn square, so one Rn cancels, and that's mv squared. So we get this relationship between speed, so how fast electron is moving around the proton. You can tell that by using this equation here, right? If you know how far the electron is, just like if we know how far a planet is from the sun, we can tell how fast that planet is moving around the sun. Same idea here. See, same idea is now being applied inside that tiny, tiny atom. So we are taking this idea that is applied to a very large objects like planets and stars, galaxies, and we are applying the same idea for the atoms. See, same basic law of physics applies to very tiny object to the very large object. So that's the beauty of science. You don't need to know the equation for all these different kind of objects. Okay. So now there was this problem, remember, it's moving around. So based on the classical theory, it should lose the energy and should soon collapse. So how do you avoid that kind of situation? So experiment shows it's not doing that. Electrons are not directly jumping inside the proton. If they were doing that, then what would happen? The atom would collapse, right? So they are not doing that. So now, how do you explain that? Emission of energy, that comes from the classical, which is not sufficient to describe what's happening. So how do you do little tweaking, modification, so that you can explain this, okay? So that's where Bohr is using this idea of quantization of energy. So in this case, remember the standing wave we saw, we can have either with the one envelope or with the two envelopes and three envelopes and so on, those standing waves. Similarly, this Bohr's model uses that idea, okay? So when electron is orbiting around, it's forming a standing wave. So when it is at one state, it's like making one envelope, and it has a certain frequency or wavelength, okay? Now, if it wants to go to the next state, then it has to have this integer multiple of that energy, okay? Just like we see, it goes from one envelope to two envelope. There is no 1.5 envelope there. So that means it fixes the position of the orbit. So if it is going around with just one envelope here, how do I show that one envelope thingy here? Just one envelope, then when it is at the another one, then what's happening is there are, these two nodes means there are two envelopes. So orbiting like this. Yeah, my sketch is not that great, but this is what it is showing. So the allowed state has to have that integer multiple, okay? And looks like it's blocking this here. So the circumference is like a length of the string that is directly related to the wavelength now. It has to be either one wavelength or 2 times wavelength, 3 times wavelength. It cannot have 1.5 wavelength and so on, okay? So when it goes from one state to another state, the exchange of energy happening is this much, and that corresponds to this wavelength. So that's how now Bohr is inserting the idea of quantumness in this classical theory to explain what's being observed, okay? So, those sketches are there, right? So we saw that, so same idea, so you use that. So that means it limits how far the electrons can be. It can only occupy, or it can be only at 1 centimeter, 2 centimeter, 3 centimeter. It cannot be in between 1 and 2 centimeter. Of course, the number I'm talking about, they are not real number, but just giving an example here, okay? So that's how it's limiting it, okay? So that's what it says. So for the ground state, use n is equal to 1. And for the other state, use n is equal to 2 and so on. And if you know energy, you can calculate wavelength. And once you plug in wavelength here, you can get how far the electron is from the proton, okay? So now you can combine this with the classical equation. You know, when something is moving in circle, that's true. So you can use this idea of quantum nature to combine with this. So here, the wavelength is coming from the electron. So it's a particle. So wavelength of a particle is given by this equation here. So mb is momentum. Mass times velocity is momentum, right? And h, you already know, that's Planck's constant. So what it is saying is, if electron is moving really fast, that means when b is very large, wavelength become smaller. It's not just the electron. So now it gives you the possibility that you can have your one wavelength. So you can calculate that wavelength. So you have huge mass. Although your speed is not that large, your mass is huge. So because of that, what happens is your wavelength when you are walking, the wavelength you produce when you are walking turns out to be very tiny, which you cannot detect. But you can detect that for the tiny objects like electrons, okay? So just solving for Rn by using this here. So that's the value of Rn one can have, okay? By putting the constraint of quantized energy and quantized energy levels. And that's the constraint. And that's the constraint there, okay? So now, when something is moving around, rather than having, like linear momentum mb, it's a good idea to write in terms of angular momentum. And we learned that angular momentum is r times the linear momentum, r times p, r cross p. in the rotational motion, we wrote that angular momentum in terms of I times omega, okay? And that is in terms of velocity, but the angular velocity. But angular velocity can also be converted in terms of a linear velocity because v is r times omega. So we can use this angular momentum idea here, okay? And it tells that the angular momentum is also quantized, which is n times the Planck's constant divided by 2 pi. And by the way, this Planck constant divided by 2 pi, we keep on getting that term a lot. So because of that, what happens is a notation h bar is used for that. H over 2 pi, that's what it means. Okay. We are just denoting h over 2 pi by, so it's telling us that angular momentum is quantized. So if something is rotating around, it has a angular momentum. So in this case, by using this quantized model, what you get is the angular momentum is quantized. You can have one value and double of that value and so on, okay? And that is related to this fundamental constant, Planck's constant. That's another interesting thing there, okay? So now, rather than me talking all the time, let's take a pause here and check what we understand or understood so far here. So for that, I have this question. So I'm opening the poll and you have 1 minute and 30 seconds to answer this question. And by the way, we're not done with that theory. I'm just pausing here to check, okay? Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here as the answer. So mostly we are getting E as the correct answer. And there are some A as well. Okay, so can somebody chime in here why that is the correct answer? If I'm thinking E as the correct answer, why am I thinking E as the correct answer? So C is 2 pi r, and r being Rn. But the problem is there is no r in this equation. So how do you go from r to wavelength? How did you do that? Can somebody help me here?
Isn't 2 pi Rn equal to n lambda?
2 pi Rn is n times lambda. So it has to be either 1 times wavelength or 2 times wavelength. So that's the quantization, right? So yeah, so you can use that here. So looks like it's gonna be, we can replace 2 pi Rn by n times lambda. And where did we write that? In the slide somewhere, right? 2 pi Rn is n times lambda, right? So that was the quantization there. So when we combine those two, what do we get? So 2 pi Rn is n times lambda, so C must be n times lambda. And n can be 1, 2, 3, 4. So there is no n times lambda, but there is 1 times lambda. Oh, looks like 1 times lambda. So looks like A is the correct answer in this case. Oh, something went wrong there, folks. Yeah, many of you thought E was the correct answer. But 2 pi thingy cancels, and A is the correct answer in this case. Yeah, sorry folks, a lot of you missed that. Okay, and thank you for help. Turns out a bit difficult question here. So how about this one here? You have again 1 minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So again, we are getting E as the correct answer, or am I looking at the same question? No, that's a different one. Question number 2, okay. Okay, so how do we explain that? Do we have equation that we can use here to explain that? So what equation we should be using to describe that? So we have 2 pi r n is equal to n times lambda we use, right? So that's a quantization condition. And here it's asking us the ratio of de Broglie wavelength of the electron in the n is equal to 4 and 1, right? So 2 pi Rn is n times lambda. And it's saying n is equal to 4. So if that's the case, then we can write 2 pi r4 is 4 times lambda. Let's say 4. For n is equal to 4, we are writing everything as 4. And now for the another one, it's going to be 2 pi r1 for n is equal to 1. It's going to be 1 times lambda 1. So it's asking us to find the ratio of this wavelength n equal to 4 to n equal to 1. So it's asking us to find lambda 4 to lambda 1, right? So that means we need to divide this by this. So when we do, what happens here? Oh, let's do right here. So this 2 pi cancels. So we are looking for lambda 4 over lambda 1 means this 4, we want to bring the other side, right? So 4 goes down there in denominator. So it looks like it becomes quarter. So you guys did it correctly, most of you. So from here, lambda 4 over lambda 1 from this equation is 1/4 of R4 over R1. So yes, it's a quarter. So now, let's get that equation that gives you the wavelength, actual wavelength, okay? Maybe this is time for a break. So let's take a break and then we're gonna go through that derivation of equation and we talk about how we use it, okay? So let's take a break here. Okay. So we are looking at an example how you can explain the experimental observation by using mathematical model. And how do you develop that mathematical model? Beginning from what you know and include the new information there to come up with the new model. So that's how physics evolves, okay? So this is a beautiful example of that. So that's why I want to show you this process. And mathematical detail is not beyond the reach. But if you don't understand all mathematical details, that's fine. Just try to, understand how things are done rather than understanding every steps. But there are going to be some main idea that you're going to be tested on rather than the derivation of this entire thing. So we left in one of the last slide, we left this one here. So that came from, this equation came from just applying Coulomb's law and Newton's law, right? For the circular motion. So now, just using a mathematical trick here because we learned that the wavelength and the Rn, the separation distance between proton and the electron, or in other words, the size of the orbit. Size of the orbit and the wavelength, they are related. So to make use of that relationship, I'm using this mathematical trick. So this and that, they are same. So multiplying, dividing by same thing, not gonna change the result. So basically this and that, it's just same. Simple mathematical trick, but see how this becomes helpful here. So what happens here is that there is m, and there is b square. So that means these two makes m square, and b square is there, and Rn square is there. So MBRN, whole thing is squared, and this is MRN square. And this is angular momentum thingy. And we learned that the angular momentum is n times h cross. So we can replace all this by n times h cross. So that's what we are doing. So this is being replaced by n times h cross. But since this is being squared, means we need to square that n times h cross as well. Okay. So now there is Rn and there is Rn square. So we can get rid of one of the Rn as well. Remember, this is equal to this. So that's the equation we have now. So now, if I cancel that and solve for Rn, then this equation gives me the distance of electron from the proton in terms of all these constants. See, h is constant, which is Planck's constant, and h bar means h divided by 2 pi. So that means it's a constant. So mass of the electron, that is constant, and K is also constant. And then you have E, that is also constant. So that means it's telling us that, okay, it's just n squared times some number. And that number being the value of R1, okay, or value of this here, the orbital radius of ground state of that electron. Hey, let's plug in the values of all these numbers here. So that is, we are saying that's A0 just for simplicity. So all these are constant. So replace that constant, all those constant by a constant. And we can compute the value of that constant by plugging in all these value. When we do that, we get this number. PM is not prime minister or past meridian. Okay, it's a picometer. So unit of distance. It's a picometer. So this is 10 to the power negative 12 meter. A picometer, 1 picometer is negative 12. So micrometer is in the order of width of a hair strand. Okay. Now divide that width into 1,000 times, that becomes nanometer. So that nano thing is already really, really tiny. And divide that by 1,000 times, and that's the pico. And so that means, in other words, that's the, you know, like 1,000th of a billion. So that's how that is. So we can just imagine, only imagine how small that is, rather than visualize it, because we cannot see the object that has a nanometer dimension with our naked eyes. Okay, so here it's 52.9 picometer. So if we were to push this, what happens? This being 10 to the power negative 12, if we were to move 2 decimal place here, it's going to be in 10 to the power negative 10. 10 to the power negative 10. So that 10 to the power negative 10 is also known as angstrom. Okay, and this is denoted by A and with a 0 or O on top of that. Okay. Oh, didn't write it. So in terms of angstrom, it is 0 is 0.529. I don't know. We can simply say it is around half angstrom. Okay. So size of hydrogen atom is about half angstrom. So these atoms, their size in angstrom. So hydrogen being the littlest, tiniest atom. Remember, more electron means, so 1 electron is orbiting there, and if there are like 2 electrons, then helium is both electrons gonna orbit in the same orbit. Once we go to the lithium, for example, 3 electrons, so 3 electrons cannot orbit in the same orbit. So what happens? Now you need higher, another one, right? Orbit. So that means size of the lithium becomes larger than the size of hydrogen, but it's still going to be in angstrom range. So as the number of electrons increase, or I should say the atomic numbers of the atom increase, their size also increase. Okay. So now let's find out the energy of the electron. Remember, we want to describe the wavelength that comes out when an electron goes from one excited state to another excited state. The wavelength is related to energy. So we need to write down what's the energy of that electron when it is at that much distance, and what happens to the energy when it goes to the another level. And another level gonna be how far? So remember, so see here, so Rn is n square times A0. So now the second gonna be 4 times farther. So now, for example, hydrogen and helium, if it is there, electrons orbiting here, that means for the lithium, what happens? The next orbit, actually these orbits are not for those cells, but it is for the excited state. So now, if it is at the, let's say, a ground state, then next first excited state gonna be 4 times, because you need to plug in n is equal to 2, and it is being squared means it's gonna be 4 times A0. So it's gonna be 4 times farther. Okay, so 4 times farther means the force required for this to keep in the orbit gonna be, needed gonna be less. That means the energy gonna be also less. So what happens? The energy gonna have different values. So we wanna calculate that. So basically, electron is a mass that's orbiting around in a field of a proton or protons or positive charge. So that means it has a kinetic energy because it's moving. So good old kinetic energy, half mv square, and the potential energy, and potential energy being the potential energy between positive charge and negative charge. Okay, so potential energy due to its being in the field of that positive charge. So we can write that and add them together to get the value. Okay, so potential energy, remember we know potential energy is K Q1 Q2 over R. So here 1Q being proton, so we are talking about for the hydrogen atom here. Another being electron, so we have this. So when we are writing it for the force, negative sign simply means direction. But when we are writing energy, negative sign means than actual, positive and negative values. So we need to stick it around, right? So that's why here we need to write it. And then this is our good old kinetic energy. But the speed depends on radius as well. So what we can do is we can write that speed equation, this mv square, in terms of a distance here, right? So remember our mv square can be written something like this. So we are just using that thing in there. It's just mathematical manipulation. But of course, it has to be valid. And we proved that can be done, right? So with this, what happens? This is also in terms of distance. This is also in terms of distance. So now we can add them. And the adding gonna be easier if we replace this Rn by this one here, simplified form of Rn. So that's what we're gonna be doing here. We're gonna be writing Rn as n square A0. Similarly, this Rn square as n square A0, but this thing has to be, whole thing has to be squared. So when we do that, what happens is now some of these quantities going to cancel, right? So that's any square thingy, that's going to cancel. A lot of things going to cancel, and we're going to just get constant again with just any square there. So all these constant except this n square, we are calling that E1, and that is the energy of the electron at the ground level in its ordinary orbit, right? So its regular orbit. So now we know that value because this E1 is all these constants here, and we know those constants. Once we plug in, what we find is we find this as negative 13.6 electron volt. And remember, this energy electron volt and joule, they are related, something like this, 1 electron volt. So this energy being small, we are writing in electron volt range. So this is the energy of an electron that is being accelerated at 1 volt potential difference. So basically it becomes 1.6 10 to the power negative 19 joule. 1 electron volt is that many joules, right? So here, if you want that in joule, of course you can do that, but this number is awfully small. So that's why we are writing in terms of electron volt. So when you start talking about energy of electrons, protons, or atoms, what you do is you write in terms of electron volt rather than in terms of joule, because joule becomes really large unit. Just like we don't measure our height in miles, right? We measure that in feet or inches, or even better in meter and centimeters. We don't measure that in kilometer. So same idea, when things get smaller, we use smaller unit, and that's what we are doing here, okay? So now, nice thing about this is that this is negative 13.6 electron volt, and we have n square. So what it means? So n is equal to 1. Means that's the value of ground state, right? N equal to 1 means n square becomes simply 1, so it's not going to change. But when we go n is equal to 2, then what happens? N square becomes 4. So this becomes 4. So for E2, okay, once we go from ground state to fast excited state, it's going to be 1/4 of that. So it decreases by, quarter. It becomes just quarter of that, and so on. So it becomes, so I don't know if you want to say it increase or decrease, because this is energy, and more negative means less value. So that means you go to higher level, it has now higher energy. Okay. So negative number decreases means the value actually is increasing. So as the electron jumping up and up means they have now higher and higher energy. So the fun is when those electrons jumps back down. So you give energy to that electron, they jump, okay? If they find suitable energy, they absorb it and they jump, okay? And then they don't even spend like, they spend less than a microsecond on that higher state. What happens? They come back down. And when they come back down, what happens? They release energy. Okay, so that released energy comes out as all this radiation, and that's what we see. Excuse me. So when you are looking at mercury tube light, there are these electrons in mercury atom. They are getting energy, electric energy, and they are getting excited, goes to higher level. And then when they come back down, they are emitting all these different wavelengths, and all together they appear to be white. So that's how we are getting light. Okay. So now here is question for you. And you have a minute and 30 seconds to answer this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. 1/3 versus 9. So let's suppose I'm thinking A as the correct answer. Am I right or wrong, and why? How is radius of Bohr's orbit Rn is related to different values of R's? So how n is equal to 1 and 3, they are related. We call that one A0 or R1, right? So how is Rn related to A0?
I said that A was incorrect because Rn is equal to n squared times the A naught constant. So when n equals 1, it's just the n naught constant, but when n equals 3, you're going to increase by a value of 9 because it's going to be 3 squared.
Hey, that's right. Yeah, that sounds right. So A is not right, folks. Yeah, looks like D is the right answer here. Thank you for help. So gets bigger and bigger, right? So no point of saying smaller here. Okay, what was I thinking? So now, so this is how these energy level diagram of this hydrogen atom looks like. So there is the ground level, or E1, right? And this is E2, this is E3, and so on. So E1, by plugging in all those constant in that equation, you get that, right? And E2 is E1 over n square, means E1 over 4. So this is 1/4 of that. And this is 1/9 of that, and so on, right? So now, what happens? Electron, most of the time, spend here. That's the ground level, okay? So that's the energy of the usual orbit. When it's not getting any boost, what happens? That's where the electron stays. Now, if it somehow gets energy, so for example, you can make hydrogen gas, put that on the tube, and then supply energy by connecting that with the battery, supplying the voltage, passing the current through that. When that happens, what happens? It absorbs some of the energy, and depending on the opportunity it gets, it may jump either here or there or there. So it depends on how much energy it grabs. So if the energy it grabs matches exactly with this, then it's gonna go there, okay? So now, immediately it reaches there, what happens? It's gonna come down there, and in that process, it's gonna emit the energy. And how much energy it's gonna emit? Remember, for this, it is negative 13.6. When it was there, the energy was negative 3.40. It went there because it was able to absorb that difference in energy between those two levels. Okay. So now when it returns, the difference is gonna give up. So that energy comes out as a radiation or the photon, okay? So you see that photon, but this energy difference is so large, the wavelength is so small, our eye cannot see it. So it goes in ultraviolet range. Is it written somewhere here? So this goes in ultraviolet range, okay? It's not visible. We cannot see it. But if it were to jump here or there and there, in that process, while coming down here, that electron may jump down here before it jumps there. So it may emit energy in two different processes. Yes, of course, it may just get down here directly too. So it's a chance, okay? And so,
Professor,
yeah.
Sorry to interrupt. I've just got a question out of curiosity. What causes the fluctuation of the electron between like energies 1, 2, and 3 and so on?
What causes the energy between 1, 2, and 3?
Like
So
the fluctuation of the electron. Is it just due to the free form motion within the atomic cloud?
So yes, it has to be forced. Otherwise, it just remains in ground state. It has to be forced means it receives energy. Okay, it has to receive energy from some sort. Okay, some sort of. So just like I said, you can put the hydrogen gas in a tube and connect current to that tube. So in that process, what happens? It may excite that electron.
The excited state. Okay, yeah.
Okay, so just like if a ball is sitting on the floor, what happens? It doesn't go to the ceiling, does it? On its own? It does not. But if you kick to that ball in right direction, then it may go higher. But what happens? It comes back down, right? So whatever energy you gave, what's going to happen? It's going to release that energy when it's coming back and hitting the ground. So it produces noise. I mean, it may produce sound. It may also produce vibration. So that's kind of some sort of heat energy, right? So it's coming out in that form. But electron, when it comes back down, what happens? It can emit energy in these different range because
in the form of light.
Yeah, it can emit in the form of light.
Okay.
That light, visible light, is going to be visible light when it lands here before coming down here. So it may come down at different steps. So let's say you hit a ball, you kick the ball in a stairs. You know, so there is this different level, there is stair, and you throw the ball up there. What's the possibility? It may come each of these steps down through each of these steps, or it may skip some of those steps, or it may just directly come down, most likely not, but let's say if it bounces from the upper one, it may come down, right, directly down without touching the middle one. So the mechanism is not exactly same, but I hope it helps you to visualize that. Okay, so it may jump up to any of these levels, and it depends on the energy. So for example, ball may go to any height depending on how much energy you supply. The difference is ball can be at any height, but the electrons can be only in these discrete state, like a staircases. Okay. not anywhere, not everywhere, but only on those. Now, once ball lands here, ball not gonna just go up there, right? So same idea. If the electron just go there, it's not gonna go up there. Rather, it's gonna just jump down here. But if the electron makes there, then it may come down and down there, or directly down there. So if it comes directly down, then it emits high energy because the difference is high there, right? And if it comes here first, then one photon here, and when it's jumping back down from there, that's another photon. So it's emitting two photons with two different wavelengths. This wavelength is going to be shorter because the gap is small. Oh, sorry, longer because gap is smaller. And this wavelength is going to be shorter. Remember, energy and wavelength, they are inversely related. E is h times f, or hc over lambda. Okay. So that's how it works. See, it's happening in picometer level. And we can tell, we can explain exactly what's happening. We can tell why that particular light, particular line we are seeing. Isn't that beautiful? Isn't that wonderful? And with all those knowledge, we have these different kind of light producing devices and so on, okay? So all those discoveries in invention started from this knowledge here, okay? So that's how things are interesting and beautiful when you can explain what's happening in the nature and can make use of it, okay? So that's how this different kind of series, so these Balmer series are the ones that jump from higher state to n is equal to 2, okay? And depending on which one they are jumping down from, they're gonna have different wavelengths. So for example, when it's jumping here, smaller gap means longer wavelength. So that means it gives you red color light. Red color photon is coming out there, okay? But if it is jumping from, let's say, higher one there, then that's when blue or purple is coming from, okay? So in that range. So here, as it goes higher, this difference is not as much. As you can see, the number gets really small, so it doesn't matter much. There's going to be just slight difference, okay? Now, if the electron can absorb so much energy so that it just skips all those steps and gets out from the attraction of that proton, then it leaves the atom. And we say the atom became ionized. So that's what the ionized ion is. Electron leaves. Why does electron leave? Because it becomes so much energetic that it can jump out of that binding energy, or bonding. So think about, sometimes I like to visualize this electron is in some sort of like, let's say, something in a well, right? Underground well somewhere. So now what happens? If somehow we can get large push, then we may escape from that well. But so in that case, we become free to wander around. And we call that electron also free electrons once it leaves the atom, making the atom ionized, and electron becomes free, okay? The same idea, free electron, that's what it means. But when it is within the potential boundary of that atom, so you can think of, okay, so wherever the atom is, this thing makes some sort of potential well, energy well, and depending on how much push they get, they may just jump up and down. But if there is enough energy, it may also escape all the way. Okay? And that's when we say, okay, the electron became free, means that atom became ionized. Now it has just positive charge, net positive charge. Okay. So all this explanation was possible by using this quantum nature, okay, discrete energy. And this is the formula we can use, okay, to calculate now. So remember, we had this Balmer's formula, one with the Rydberg constant. En is equal to, I think it was like 1 over wavelength, was some number here, some constant R, and 1 over 2 square minus 1 over n square, where n is greater or equal to 3. So that's what it's talking about. It has to be n is equal to 3 or bigger. When it jumps down to n is equal to 2, that's when we see that wavelength that's visible, okay? So that's what that equation was. And where is 1 over wavelength? See, this is, energy is h times f. And in terms of wavelength, it becomes hc over lambda. So there is 1 over lambda here. You see that? It is 1 over lambda right there. So this was just the partial equation of, this one was the partial equation of this full equation there. Okay. So now here is question for you about these electron jumping. So you have 1 minute and 30 seconds to answer this question. So let's suppose somehow the electron had jumped up there, right? So now how many lines are possible? So for example, one line is when it jumps here. That's one possibility, okay? So how many possibilities are there? That's what you want to explore. You want to draw and answer this question. So 1 minute and 30 seconds for you. So you need to draw lines, okay? If I were you, I would draw them. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's draw. So one possibility is it goes directly down, right? So it emits this. This is going to be the most energetic photon, means it's going to have shortest wavelength. So that's line number 1. Another possibility, rather than just coming down directly, let's say comes down here and down here in 2 steps. 2, 3. So I don't think I need to keep drawing those photons. So that's 3 already. Now what other possibility we have? It can just come down here.
Dr. Damana,
Yes.
Why are they going down if in the question it says they're being excited to the N4 state?
Yeah, it's sitting there. Now, after that, what happens? Remember?
Isn't it sitting at 1 and then it's being excited to 4?
Yeah. So it's usually lives there. It's here. It's here. It is its home base, right? It's like a home. So it goes out for a while, and then eventually it comes back. But while coming back, there are different possibilities. So what are the possibilities it's talking about? So from
Got it.
excited state, it comes down. It doesn't stay in excited state more than a microsecond, okay? Oops, I
Okay.
erased
Thank
that.
you. Thank you.
So yeah, I'm glad you asked. So that's how the lights are emitted, okay? That's how light comes out. So it's that explanation. It's not a simple thing there, okay? So now I missed all those. So 1, 2, 3, 4, 5. Is there other possibility there? Came down there, down there. So what if it comes down here and down here? And this thing is already there, so it looks like that possibility not gonna get us anywhere. Because this was already there. So this cannot be new thingy here. So this and direct down. So it looks like we already took care of all of those, did we?
We didn't do 3 to 2. Wouldn't 3 to 2 be a new possibility?
3 to 2. Okay, so 3 to 2, a new possibility. So yes, but after 2, it has to come down, right? It cannot just stay at 2. Remember, for every possibility, it has to arrive to the down there in the ground state. So if it does, then it's going to be, let's say it's going to do that. So this thing is already counted. So looks like, yeah, we may have that one more possibility there, right? In the process, it came like this. Rather than going through this, this is counted for, so we don't need to double count. This is already counted for, but we did not count that. So yeah, that's another possibility. Thank you. So it looks like it makes total how many? All 6? Yeah, so it goes all the way 6, looks like. Hey, you guys are very smarter than I am. Figure out quickly. So now, let's also do a little bit math here. Oh, we kind of ran out of time. So you're gonna be just using this formula here. Oh, formula is right there, okay? Maybe I'll do this as a part of also a revision next time. And you may also want to read through these slides here. Oh, now to explain this, now you can explain this using this atomic model, okay? And there are these new things, those were interesting, which looks like I'm not going to be covering, but if you are interested, please read through that. Those are some interesting stuff, okay? But let's wrap it up here. Yeah, we went a little bit over time. Sorry about that. Okay, I'll see you guys next class.